Okay, so we were talking about the Fourier series formula, and specifically why do the equations for the Fourier series coefficient calculation, why does that equation differ from the formula for Fourier transform? And we saw that they differ in two ways. One is the limits are uh, changing. They become 0 to t naught, where t naught is the period in seconds. And then you multiply the integral with 1 over t naught. Now you may ask that we just asked, you may wonder rather, that we just asked a curiosity question regarding my Fourier transform. Uh, I mean, why are we going to Fourier series, and why are we talking about periodic signals and opening up this whole new Pandora's box? Um, then some of you may even wonder that this such questions should not even have been asked, because now will this be part of our syllabus at the end of the semester exam and all that? Okay, so those are practical questions that you may have. The answer is yes, yes, this will be part of your syllabus, is part of your syllabus. Uh, that is the direct answer, but more fundamental answer. The reason why I am spending time on this topic is because this function, my Fourier transform, that you have used in lab 5, but more importantly, the FFT function that you use, MATLAB's FFT function, that is a very powerful function. And understanding what FFT does, the concept behind that FFT function, is going to be extremely useful to you as you progress in your academic and then subsequently professional careers, especially if you take up communication systems or signal processing, or even if you do machine learning or artificial intelligence. FFT is everywhere, and it is better to fully understand what FFT does in a very conceptual manner. And that is the reason why I thought that we'll spend some time on this topic. The consequences that yes, this kind of becomes part of your syllabus, but the important thing that I would like you to focus on is just expanding your understanding regarding the Fourier transform function as it is implemented algorithmically by this FFT function. So what is the FFT function is what my focus is right now to show to you. And why are we talking about Fourier series, and why are we saying that if the signal is periodic with some period t naught seconds, then the Fourier series formula becomes different from the Fourier transform? So let us get to that now. You see, whenever we use FFT function in MATLAB or in Python or in any other programming language, we necessarily are dealing with samples of a time domain signal. Uh, we cannot have continuous time signal. So first of all, the uh, signal has to be sampled at some sample rate or sample duration t of s. Second thing is that our function in computer cannot take infinite number of such samples. There has to be some finite number of samples that is given as the input to this FFT function. And in our case, we had a variable called n sample. In general, it is some integer n number of samples that we have from time domain. Basically, capital N samples of the signal W of n. And now, let us pretend, as of now, let us pretend that our signal is not only discrete in time, but additionally it is periodic in time. And somehow let us pretend that the period of the signal is essentially this n samples, capital N samples. Or when you multiply n with t of s, where ts is the interval between two samples in seconds, what you get is the period in seconds, t naught. So t naught is n times ts. So now we are considering a discrete time signal whose samples are available to us, and we are assuming that this signal is periodic in the time domain with period of t naught seconds, and therefore we have capital N samples total of this signal where n is t naught divided by ts. We will assume that our ts has been carefully chosen so that when you divide t naught with ts we get an integer n. Now this is where the thinker's paradise comes. Okay, I mean this is where you have many such duality going on now. See, the signal is sampled in the time domain. And so as soon as you see the sampling in time domain, you have to immediately think of frequency domain as becoming periodic. What is the period in frequency domain? We have seen this earlier. It is 1 over Ts, where Ts is the sample duration. So basically this signal has a periodic structure in the frequency domain, and its period, the base period, the fundamental period, you can take it either going from negative fs over 2 to plus fs over 2, which is what we did in my Fourier transform function, or you can take the base period as going from 0 to fs, which is what MATLAB's FFT does, by the way. So let us continue with MATLAB's FFT nomenclature and say that we are now going to evaluate the Fourier transform over only the fundamental period, which makes sense. We don't need to do anything else. If we get the Fourier transformation nailed down over this fundamental period, then we have solved the problem, because we know that the rest of the periods are just going to be copies, the repeats of this fundamental period. So all we need to do is evaluate the Fourier transform over 0 to fs. Now let us take a moment in further understanding this periodicity that happens in the frequency domain. See, whenever we sample in time domain, because the frequency domain becomes periodic with a period of fundamental period of 0 to fs, the way to think about this, and by the way, this I read about this in a nice textbook by Roger Penrose. He is a very prominent, eminent physicist from Great Britain, and he has written a number of books on physics. Some of them are easy to understand, and in one of the books that he has written, he describes that whenever you are dealing with periodicity, think of it as a wheel. Infinite duration signals, which are periodic in nature, can be conceptualized as rotating on a wheel. So what do I mean by that? Without this sampling in the time domain, the frequency axis is continuous, going from minus infinity to infinity. But as soon as we sample with a period of interval of t of s seconds, that frequency axis turns into a wheel. That is what I am showing here. This is the frequency in the continuous time domain. It goes from negative infinity all the way to positive infinity. But once we sample in time domain, this only the base period remains. Either you can call it 0 to fs, or you can call it minus 0.5 fs to 0.5 fs, or you can define your own base period. But the width of the base period will be equal to the circumference of this circle, which is f of s, 1 over t of s. And then the rest of this infinitely long frequency axis just gets rotated on this wheel. What it means is that 0, f of s, negative of f of s, negative of 2 times of f of s, and so on, they all map to this point over here. Same way, 0.5 f of s minus 0.5 times f of s, all of those locations here, they all map to this point. And then the remaining part becomes the rest of the circle. And so when we evaluate the Fourier transform, we are we can evaluate either from 0 to f of s, which means we are going around the circle like this, which is what FFT function does, or we can evaluate from negative zero point 0.5 f, zero point 0.5 of f of s, which is this point here, remember. So we are going from the negative highest frequency, which is negative zero point 0.5 of f of s, and then we are going towards 0 hertz here, and then we keep on increasing and then go back to 0.5 of f of s, which is same as negative 0.5 of f of s. This is the convention that has been used in my Fourier transform. Okay, so that is the implication of sampling in the time domain. But remember, we are here considering not only that the signal is sampled in time domain, but also that it is periodic in time domain. And so now remember that whenever a signal is periodic in time domain, what happens in the frequency domain? Periodicity in one domain translates to, I don't need to say this aloud, you should know this answer yourself by now, that the periodicity in time domain translates to sampling in the frequency domain. Sorry, periodicity in time domain translates to sampling in the frequency domain. And so therefore, for this particular signal, this Fourier series coefficient, which was an integral before, a continuous time integral, because of this sampling in time domain, it became a summation. The frequency became discretized, and this discretization is happening because of the periodicity in time domain. But additionally, the Fourier series formula that we have seen earlier, the integral got replaced by a summation because there was discretization of time domain as well, because we are having sampling in time domain. So when you discretize this integral, it turns into this summation. This d of t becomes t of s. This is our sample duration, the smallest interval in time, t of s. T naught becomes n times t of s. This we have seen already. T naught here is n times t of s. This T naught now in the discrete time domain translates to only capital N samples, and so 0 to T naught becomes 0 to n minus 1. So this index n, which is the time domain index, goes from 0 to n minus 1 because capital N is the period in samples in the discrete time domain. Wt obviously becomes value of n, and this t becomes t of n, but t of n is nothing but n times t of s. T of n, the nth sample, is located at n times t of s. And so therefore this formula turns into this formula. But remember that f0 times t of s is nothing but 1 over n. f0 times t of s is this capital T naught is 1 over f naught, and so f naught times t of s is 1 over n according to this formula here. So here what I did was I replaced f naught times t of s with 1 over n. This t of s and here they cancel out, and so now I get the formula that is shown over here. Okay, what is to be noticed in this formula is that all it has are integers. Everything is here is integer based. The frequency and the time, they both have been abstracted out. Although we will refer to n as a time domain index, it is just an integer that goes from 0 to n minus 1. This k is also an integer. Remember, this we did way back here, that k is an integer. And the reason it is an integer is because we have assumed that our signal is periodic. So k is also an integer. And so this entire formula is based on integer. And there is 1 over n term right in front of it. So this is the reason why we have that 1 over n sample multiplier at the output of my Fourier transform. We have said k is an integer, but what is the range of k? By the way, k represents frequency domain, n represents time domain. Although both are integer, their semantics are different. So what is the range of k? Remember, we are considering just the fundamental period 0 to f of s. Why we are considering the fundamental period? Because the time domain has been discretized, and so therefore the frequency spectrum has become periodic, and we are considering the periodicity from 0 to capital F of s. But we are also saying that even the frequency is discretized. Why is frequency discretized? Well, the frequency is discretized because we are considering the discrete time signal to be periodic with a period of t0 seconds. When the frequency is discretized, what is the smallest frequency separation between two samples in the frequency domain? It is f0. And so therefore, what is the range of this discretized frequencies that we have to consider? Well, that range has to be only from 0 to f of s. That tells us that the discretized frequency has to be 0, f0, 2 times f0, all the way up to capital N minus 1 times f0. Therefore, k has to be from 0 to n minus 1 as well. We cannot include k equal to n in this set. Why not? Because remember, 0 is equal to f of s. So 0 times f0 is equal to n times f0. And so k equal to n is same as k equal to 0. So the minimum value of k is 0 and the maximum is n minus 1. If you look at my Fourier transform function that I have given to you in lab 5, the mistake, the bug, whether it was deliberate or not, I will leave it up to you to decide. The bug was that k was going from 0 to n. That was one mistake. The second mistake was that k was not even integer valued. If you put a breakpoint within my Fourier transform function, you will see that k was not 0 to n minus 1. It was going from 0 to some 1.1 or something, some non-integer number, 2.2 and so on. And then it will go all the way up to capital N. But that is evidently not the right thing to do, because what we want to do is we want to maintain uniformity in the samples in the frequency domain, and those samples have to be integer multiple of f naught. They cannot be a non-integer multiple of f naught. When we talk about non-integer multiple of f naught, we are not doing Fourier series anymore. Remember this. Alpha, where alpha is not an integer, should not be our should not be in our consideration. So essentially what we have done is that by considering the signal to be both sampled in time domain as well as being periodic in time domain, we have made the frequency spectrum also to be sampled as well as periodic. The way to think about that is in this manner, that the time domain periodicity, because the signal is periodic in time domain with a period of t naught seconds, translates to sampling in frequency domain, which is nothing but our Fourier series formula that we have seen earlier, that sampling is a multiple of f naught, the harmonics which are multiple of f naught. So the samples have to be always f naught 2 times f naught all the way up to n minus 1 times f naught. Why not any more than n minus 1 times f naught? Because our frequency domain has become periodic, and the period is equal to f of s, and if you make this samples any more than n minus 1 times f naught, you get into the second period, not you are out of the base period already. The sampling in time domain is causing that periodicity. The samples are also uniformly obtained, just like the frequency samples are uniformly obtained in the time domain. Our samples are obtained at 0, t of s, which is 1 over of f of s, 2 times t of s, up to n minus 1 times t of s. So you see there is a remarkable similarity between these two, f naught and ts, the sampling duration in time domain and the sampling interval in the frequency domain. They are kind of analogous in nature. But even more surprising is that this f naught is inverse of n times ts, and this t of s is inverse of n times f naught, which is f of s. So there is a tremendous duality going back and forth between time and frequency domains. And that is what is summarized over in this slide. The input to FFT function of MATLAB or our my Fourier transform function are capital N samples, and those samples are t of s seconds apart. F of s is 1 over t of s, and it indicates the sampling duration in the frequency in the time domain. So inverse of t of s, inverse of the separation in the time domain, becomes the period in the frequency domain, f of s. This we have seen earlier. Furthermore, because we are assuming that the signal is periodic in time domain, the period becomes t naught, which is n times t of s. And the inverse of t naught, which is f naught, becomes the sampling interval in the frequency domain. So there is a very intimate relationship between what is going on with time domain and frequency domain when we consider discrete time periodic signals, for which our Fourier transformation becomes discrete time Fourier series, or DTFS. When we use FFT function of MATLAB, we are actually doing DTFS. By the way, this is I took this periodic nature of time and frequency, and like what has been suggested by Sir Roger Penrose, I turned it into a wheel over here. Okay, you may say that all that is fine and good, but actually our signals may not be periodic in time domain. Well, even if they are not periodic in time domain, we are just going to pretend that they are periodic in time domain before we give those samples, those capital N samples to FFT function of MATLAB. The reason we are forced to pretend that the signals are periodic in time domain is because if we assume that the signal is not periodic in time domain, then this W of f, this f, variable f, becomes analog valued. And we cannot have any computer algorithm that can evaluate W of f over continuous range of f. Computer cannot deal with continuous variables. And so therefore we have to discretize f. As soon as we discretize f, eventually we are led to periodicity in time domain. And so when we use MATLAB's FFT function, actually what we are doing is discrete Fourier transform, which is what also my Fourier transform does. And effectively we are evaluating DTFS. DTFS and discrete Fourier transform are one and the same thing. The only difference is that for DTFS, our assumption that the signal is periodic in time domain with a period of t naught seconds is actually correct. For DFT, we are just hoping that it is correct. It may not be correct. Okay, so that is where we will stop this video.